Hello and welcome to Risk Analytics. In this example, we're going to look at airline reservation, and it's a great example of how to use binomial distribution in simulation. So we're going to walk through this lecture. The key part here is how we use a binomial distribution for, like, if someone shows up. There's a 10% chance of somebody showing up. My name is Hari Rajagopalan, and I will walk you through this lecture. So let's take an example of Piedmont Commuter Airlines. This is a small regional airport and a major hub. It flies between a small regional airport and a major hub. The plane has 19 seats, and often several are vacant. And you can use Florence as a great example of this. So tickets cost $150 per seat, and there's a 10% probability of a sold seat being vacant. So I could sell the ticket, 10% chance of a no-show. If PCA overbooks, it must pay an average of $325 for any passenger that gets bumped. So if you turn up and there is no seat, you got to pay an average of $325. Demand for the seats is random and it's shown in this table, right? So sometimes you have 14, there's a 3% chance, 15, there's a 5% chance, and so on, of 14 to 25. So the question is, what's the optimal number of seats to sell? Now, an easy way to do it is to sell 19 seats. You have 19 seats, you sell 19 seats, you're going to get $150 per seat, and then you multiply 150 times 19. That should come to about $3,000 per day. I mean, 3,000 less than 150, so that'll be $2,850 per day, and you're done, and you walk away with that money. No risk, right? No bumping people. But if only 14 people show up, then you fly with 5 seats empty, and you could have made that extra money. You could have essentially sold 24 tickets, 5 people not showing up, and you could have got that extra money. So this is called yield management with airlines. This is called yield management. They often sell more tickets than they have because there's always a chance that people are not going to show up. So how are we going to model this problem? Let's go ahead and start the model of this problem. So first is, let's put the inputs we have. We have 19 seats available, tickets per seat is 150, probability of no-show is 10%, cost of bumping is 325. We are also given the probability of demand here. This is essentially a discrete distribution. If you add these probabilities up, it should come to 1 or 100%. So your decision variable is how many reservations should you accept? 19, 20, 25? No good doing it more than 25. You should do at least 19, right? So the stochastic variable is your seats demanded, right? And so you're going to use this PSI discrete, and you're going to look at the demand and the probability. And the calculated variable is your tickets sold. So how you're going to use tickets sold is if your reservations accepted is more than the seats demanded, then seats demanded is your tickets sold. If reservation accepted is less than the seats demanded, then tickets sold is the number of reservations accepted. You should not use the if function. Remember, the if function causes a heavy load on the optimizer and other things. So essentially you're saying, hey, whichever one is less, right? Whichever seat demand, whichever one is less, you're going to select. So you can use the min function. Once you get that, the calculated variable, you are going to do the stochastic variable. How many passengers are going to board? So remember, each ticket you sell here has a 10% chance of no-show. So you can use binomial distribution. Number of trials is the number of tickets sold. Probability of success, which is probability of people showing up, is 1 minus the probability of no-show, which is 90%. And that would give you the number of passengers to board using binomial distribution. Then you can calculate the ticket revenue, right, which is tickets sold multiplied by the price. Cost of bumping will be cost of bumping 325 multiplied the number of passengers which are bumped. So how many passengers are bumped? It's 0 if passengers to board is less than seats available, right? If you have this value is 19 or less, there's no bumping. But if this value is 20, 21, 22 is more than that, then the difference between the 19 and this, right, is going to be how many passengers are going to be bumped. And that'll give you marginal profit, right, which is your forecasted variable that has the PSI output. And let's go to Excel now to see how we're going to model this problem. This problem, because you have a decision variable, you can use a data table and you can use an optimizer. And I'm going to show you in Excel how you do that. Okay, let's look at how we set up the problem. The input is right here, right? This is your input. Seats available, tickets per, all of this is given to you. There's no issues here. Your decision variable is how many reservations should you accept. That's your decision variable, right? So now we are coming to, here is the probabilistic. These two are probabilistic and this is a calculated value, right? So what is the probabilistic value? How many seats are demanded? And this is a discrete distribution. You can see here the total probability is 1. Expected value is your weighted average, right? So you multiply 14 times the probability, 15 times the probability, add them all up, and you're expecting to get on average about 19.32 on average, right? So between 19 and 20, mostly skewed towards 19. So we've got this now, and then you can calculate your ticket revenue, which is simple. But the cost of bumping, you'll only get cost of bumping if passengers to board is more than 19. So you got to take the difference between passengers to board and 19. And if it's negative, then it's going to be 0. If it's positive, the difference between it, then you multiply it by 325. So we're going to use the max of 0 and then the difference between the two. If C12 is greater than C14, that'll be higher than 0 and it will multiply. If it's a negative number, which is C12 is less than C4, then it will take 0 and it will multiply by 0, which will give you a 0. All right. And this is your PSI output. So you can see here, this is your binomial distribution, and it says, okay, so many percentage of time I get 13, so many percentage of time I get 14, so many percentages of time I get 15, 16, and so on. You can actually see how the data is coming through, right? And you can check on what this cell is doing. You can also look at this PSI discrete. And you can see here, so many percentages of time you get 14, 15, and here's according to the distribution, okay? And your marginal profit now. So here's your marginal profit. You can see you got an average, you got a standard deviation, and you can look at how the data is distributed also. Because this and this are discrete, profit looks a little discrete also. So once you have this discrete part, you've set it up, you can then calculate, you can run a simulation and calculate whatever you want. Now I've set this up because it makes it easier to convert it to a data table. So simulation is first simulation, reservation accepted is 19, and I use PSI min, right? You select the PSI output file and the number of the simulation number gets the minimum 20th percentile here. So you put 20% and the simulation number. You get the mean. You can even get 50th percentile to get the median, 80th percentile here. You can see, so here's the mean. You can get the standard error, right? You can even build confidence intervals if you want to. It's pretty easy. So you already know how to do this. So you can do that. And now we want to copy this, right? And build a data table. Once you create a copy, you can go to data table, go up here and look at PSI sim param. So you're looking at between, there's no reason to look at optimization, the decision variable between 18 or 17 because you have 19 seats. It doesn't make sense to sell less than 19 seats. So let's look at 19 to 25, right? So we're looking at 19, 20, 21, all the way up to 25. So that's 7 different simulations, right? So you've got to go here and put 7 when you run it, okay? Also, you've got to create 7 simulations here, and reservations accepted. You can put the number. You're not going to use this. It is this you're going to use, and then you basically copy this. If you have the $sign fixed, you can just copy this whole thing down here, and you can run it. Right? If you run it, you'll run it 7 times. Nope, it's not running 7. Let's see what's going on. All right, let's make sure it's running 7 times. Yes, now it's running 7 times. And you should get, as you can see, your average is increasing. 19, 20 tickets, 21 tickets, it's increasing. And then 22, it drops again, your average profit drops. So 21 seems to be the best solution. But is it really the best solution? Let's run an optimizer and make sure. So for optimizer, and you can even chart this using this. Look at this. You can kind of chart and see what's happening. Here's the 80th percentile. Your minimum kind of is flat until 23 and then it goes down. Your maximum kind of then flattens up 24 and 25. Here is your 20th percentile and your 80th percentile, and here's your mean. It's kind of a nice little graph. You can visualize the problem. So remember, when you want to optimize, don't copy the data table. Go back to your original simulation, copy this, create the optimizer, because this should no longer be a formula. You cannot have PSI SimParam, right? You cannot have PSI SimParam. Here, you're just going to have to put the value again. So you just copy the simulation, and under the optimizer, you are going to maximize your average. Remember, this F20 optimization is not the one with the PSI output. A lot of you make that mistake and you will get an error and you will get it wrong and you'll get a 0, right? It has to be your average profit. It has to be a statistic that you optimize. Your decision variable is the reservations accepted, and then your constraint is that this is going to be anywhere between, it can be between 19 and 25. It's not going to be 14, but I've just run it between 14 and 25. And this is an integer. You can't have decimal values. And when you run it, you'll get 21. And it'll take some time to run, so we won't do it here. But when you click this and run it, this will come out to be 21. Okay? And that's pretty much it. So this is a great example of where you use discrete distribution and binomial distribution.